Hello everyone, my name is Marcelo de Castro and I'm going to present multi-time scale modeling of a STATCOM and a power grid for stability studies using Modelica. This paper was co-authored by Luigi Vanfretti and it was presented at a first workshop on open source modeling and simulation of energy systems on April 5th, 2022. This presentation is divided into 7 parts: the introduction with the background information and the motivation behind the study, the interface description, which allows us to perform the simulations presented here, the STATCOM model with its internal structure, the controller description, a section about the studied systems, the results section, and finally the conclusion and future work. And in the present context of a transformation in the energy sector, the electric power system has increased in both size and complexity, especially considering all the inverter-based resources that have been connected to the main grid. And this new complexity can actually impose challenges in many of our current modeling and simulation strategies, limiting our ability to perform proper studies that enable the anticipation of failures and the insights into improving this power system. This is a clear opportunity for us to assess the usage of modern tools, right, such as a multi-time scale approach to study such complex systems. And phasor-based or RMS systems and electromagnetic transient or EMT models are usually studied separately, and their simulations are conducted in different tools which seldom communicate with each other. This is mainly because they have nearly incompatible timescales. So RMS are usually used to study transient stability phenomena in transmission and distribution systems, while EMT are used to analyze dynamics that are much faster, such as power electronic devices and inverter-based resources. However, the current scenario in which power electronic devices are more and more common in the power grid every day, it is important to study the systems in a coalesced way, composing heterogeneous models that can be used for simulation and analysis of modern power systems. One solution to interconnect these fundamentally distinct models is to create hybrid interfaces enabling co-simulation approaches. And these strategies are numerically efficient, but they do not allow systems to be studied together. However, by using hybrid interfaces implemented in Modelica, as we propose here, it is possible to unify these different systems at the equation level using the same modeling paradigm, meaning that EMT and RMS systems could be not only simulated, but analyzed, linearized, and studied all together. And to do so, we use an interface bus that has 2 transformations that should be noted. So we have the voltage phasor to wave transformation and a current wave to phasor transformation. The wave domain will recognize the phasor-based representation as a voltage source, and therefore it is necessary to transform the phasor voltage magnitude and angle values into a 3-phase wave source. Since we are using an equivalent positive sequence phasor, a set of balanced 3-phase waves is generated here. However, if we want to include any imbalance, we can actually just put as a time of proportion or something like that, and an unbalanced set of 3-phase wave will also be generated. On the other hand, the EMT subsystem will look like a current injection to the remainder of the phasor-based system, meaning that it's necessary to filter out the fundamental component of the current waves and to calculate the positive sequence equivalent phasor in per unit. So first, let us start with the voltage phasor to wave conversion. This conversion is quite direct, and we can use the Cartesian representation of phasors from OpenIPSL to find the magnitude, angle, and frequency deviation from nominal value that are used to compose, in this case, a balanced set of 3-phase waves. The current wave to phasor representation, however, is a little bit more complex because it uses second-order generalized integrators as filters that allow us to find the fundamental component of current waves, which are then used to used in synchronous reference frame-based PLLs to create positive sequence equivalent current phasors. An important feature is the tuning of the second-order generalized filters. As shown in the bottom figures labeled A and B, different filters will allow a different sideband frequencies to be included in the phasor calculation. And these sideband frequencies might be of interest because they actually represent the dynamics of controllers that modulate the amplitude of current waves, for example. And it might be of interest to let those frequencies interact with the phasor-based system, right? Since we want to perform a coalescence study. So this second-order generalized filters, or SOGI, are then associated with the synchronous reference frame, or SRF, based PLL. PLL stands for phasor locked loop, phase locked loop, sorry, enabling us to, so this actually enable us to calculate the positive sequence phasors for the currents. And the entire conversion can be then summarized in a 7-step procedure. So the first 2 steps tell us how the 3-phase current waves are filtered for the fundamental component extraction. Steps 3 and 4 concern with the calculation of a positive sequence component from the extracted fundamental component. Finally, steps 5 and 6 are related to the calculation of angles, which are used to correctly calculate the current phasor as shown in the 7th step. In order to test this interface in Modelica, we are going to represent a 3-phase voltage source converter connected to a DC bus capacitor, which will act as a static compensator, or STATCOM, in our studies. The STATCOM is represented in its full switching state in Modelica, enabling us to test the interface in the presence of PWM-generated harmonics. And the DQ mathematical model of the STATCOM is presented in the lab together with the capacitor dynamics. And these equations are actually used to create the usual control, which is divided in 2 main loops. So the first is the inner current control loop, in which we have decoupled DQ variables that can be controlled using simple proportional integral regulators. So this inner loop is significantly faster than the outer loop, right? And the outer loop actually controls the DC bus voltage, which is the capacitor voltage. There, we can also design an adequate proportional integral regulator, enabling us to set appropriate speed and damping requirements. We then assemble a small SMIB system, SMIB standing for Single Machine Infinite Bus System, using the OpenIPSL library, as shown in the figure on the lower part of the slide. And note that on bus number 2, we actually have the interface placed there, which is then connected to a STATCOM system modeled in its electromagnetic transient approach, or EMT approach. So the entire system is simulated for 5 seconds, and we want to observe how the change in reactive power injected by the STATCOM alters many aspects of the system. As one can see, the bus voltage magnitude where the STATCOM is connected increases. Of course, as expected, as we see the modulation indices changing without any saturation. In addition, it's important to observe that the change seen in the beginning of the simulation is due to the interconnection of the STATCOM and does not reflect in any sort of unstable behavior. We can also observe on the upper right figure that the infinite bus reduces the reactive power support now offered locally by the STATCOM, which can also provide fast responses to faults occurring near the site. Finally, when we observe the DC bus voltage value shown in the right lower figure, it is possible to conclude that its regulation was well performed, allowing less than 1% variation, even during the large step variation, reference change in the reactive power injection. As conclusions for this work, we can cite that the implementation of the hybrid interface was successfully done in Modelica, since a multi-timescale model of a STATCOM and an SMIB system was simulated in Modelica-compliant tool, in this case, Daimola. It is worth noting that the strategy presented here unifies both systems at the equation level, allowing not only simulation, but an integrated analysis, Therefore, the interface can be used as a magnifying glass, allowing us to increase the level of details in certain parts of the grid as required by particular studies. And as future works, we want to leverage this unification to design proper controller strategies for power electronic devices, but now considering the entire power system, which is represented using their positive sequence equivalent models. We would like to express our gratitude to Dominion Energy and to the Center for Ultra-Wide Area Resilient Electric Energy Transmission Networks, or CURRENT, for supporting and sponsoring this work. Thank you so much for hearing to this presentation. And should you have any questions, please feel free to reach out to me at the email address listed at this slide.